on this computer. I think it should be fine. Yes. So this is the class. Basically, this is about information theory and probabilistic programming. And and this, I guess, a little bit history of the class. I started as like an information theory class, but um, I included more and more like Bayesian influence that kind of materials into the class, and I guess it's more appropriate to change the title. I thought of like what kind of title is good, then eventually pick this one. I guess it's hopefully it's more attractive to students, and so the parts about probabilistic programming is like uh, kind of like is related to how you can write program to do some of this Bayesian influence. So I won't get into like really any particular probabilistic programming languages, and will more like high level, I say. But at the same time, like I would kind of like expect you guys to learn, because like it's just like I guess if you some of you guys like have taken my class, some other classes, let's say computation and also like deep learning, um there are lots of like packages like out there like to and there are like all kind of packages. So it depends on like which one, like everyone have different preferences. So if I just pick one and say, okay, we'll use this, then I don't know, someone may like it, someone may not like it. Instead, like um I think like you all can pick whatever packages. um Unlike deep learning, I guess like for deep learning, like mostly you see like we have TensorFlow, and also like PyTorch is more or less dominating the entire kind of like realm of like packages. But here, like it's more diverse. Like there are different packages, and uh, I will mention some of them, and all of them are quite easy to learn, I would say. And it's actually um it it'll be more, I guess, like more appropriate like to for you guys to learn it yourself, like rather than because like it can be quite boring, like whenever like someone is going to talk about just a package, and then okay, here is how to write a for loop and so on. And the tutorial as very well written, and also there are like video tutorial also online as well. So I don't think I can do a better job than those tutorials. So I will more or less like leave you guys to pick whatever languages you like. And instead, like I would kind of like um basically we'll have a chance. Maybe I should go to like okay the website. So and with the website, like I also put up the website link like on Canvas, so you're able to find that. So I more or less copy most of the stuff like from the past offering. I changed only a tiny little things like uh in terms of, I guess the major change I did is I lowered the in-class participation. Um it turns out that like, I guess the 20 I used to have like 20% like extra credits. It seems to be uh a little bit too much. So I scaled down it a little bit. So here is more or less the grading. You see like we have midterm homework and presentation. So presentation will be like what I just want to mention is like you can talk about packages. This will be a chance for you to study, and at the same time you're going to uh, have have a chance to present it to your peer. And usually like it's much we at least for me, I learn much more like just talking about the materials than like listening to someone else talking about that materials. So I hope that will work for you as well. And so the in-class participation, if you are kind of like taken my class before, I have this is more or less just because we have this video offering, it can become quite boring, and it's very hard for me to get interaction from you guys to know whether like you are following the materials or not. So therefore, like I will kind of like regularly or irregularly, like ask some questions, and then like you can just like kind of like respond like on your chat, either privately or publicly, and then I will just tally all the results. Basically, like wherever you give a response, you get 1 point. If you get response a correct response, that would be 2 points, something like that. Very simple scale. And then like by the end, everything will be normalized to 10%, basically. Like for all the questions will normalize to 10% like of the total. So that will be extra credit. You don't need that like to get an A, basically, or like to get like 100 points. Like if you are doing really good for the West, I would say like midterm can be the most. I'm not sure it's challenging or not, but my experience is like this can have a large variation in terms of the. I have a large normal distributions. Like some students are doing really well, close to like 100 points, like, but some of them only get like 10, 20 points, something like that. So but either way, like if you participate everything, you should get more or less like yeah, kind of like I guess like if you get like 10% for here, the rest you're doing okay, have like some points here, you more or less can get an A. Actually, for the last times, I need to adjust this because everyone got an A. I think it's a little bit over kind of like yeah inflated the grade, so I guess I need to adjust that a little bit. So and that's the things like for the other parts I present, as I already mentioned, presentations, homework. I had 5 homeworks last time, so and more or less some of that is a probability, like related to probability. Okay, probabilities, and some of them um um I would say like I forgot, like I need to dig it up again. There's some programming exercise, but the programming is as I mentioned is it's not package dependent, so you can do whatever tools you use. You can even use MATLAB or like Python or like just pure Python. I mean, like does not use any packages. And but um but I would another thing is like if you are new to Python, I would really recommend start learning Python, because like if you see like all these packages out there, not just for this like probabilistic programming languages, uh, and also like for deep learning, let's say like all of them have like Python API. So, but very few will have like let's say Java API and so on. So, this even fewer like have like MATLAB, let's say. So, of course MATLAB has some offering from them. Like, it's like kind of uh what is that word, like not open source, something like. But yeah, Python is definitely something like good to know. So therefore I highly kind of like encourage you guys to learn Python. And in the website, like I put up some link there that could be helpful. Like there's some Python materials. I kind of like update the link. I saw that some of them used to be that link. I just update that. If you're already familiar with Python, sorry, MATLAB, then maybe actually whenever I talk about Python, usually I mean Python slash NumPy, because like NumPy is like a numerical package. It's like similar to MATLAB, so that like you can play with like matrices like more easily. Like you can just create object as matrix and uh, and manipulate that like very easily. Like for example, you can multiply a matrices together just using one command. And if you're already familiar with MATLAB, then that's definitely you can take a look of this one. It'll be good for you. Just like translate MATLAB into NumPy. Like some of these commands you're probably already familiar with. So you can check that like what's the corresponding commands in Python slash NumPy. And if you're really new to any kind of languages. I guess you can just get into this dive into Python. But I would say like there's lots of way to learn Python. So I would just leave that to you. And so that's more or less logistic. And then maybe get to some, this is like some objective of this course here. I already like mentioned some of that. Like, so I want to cover some basic information theory that is actually useful, like not just in communications. Like information theory, like is historically was single-handedly uh, kind of built by Shannon, Claude Shannon, and he was a communication engineer, like, slash mathematician, slash electrical engineer. So um, but I mean, of course, like therefore there's some influence of like electrical engineering and also like communication engineering to information theory. But like it is also used like in many other disciplines. And for example, the idea of like entropies, you see that like it's occur everywhere, like in for example, in machine learning, you see there's cross entropy there. So we could get deeper into those. So then you will come across the term like cross entropy. Let's say in machine learning, you have deeper idea what that means really. And also, like as I mentioned, like a closely related discipline is like doing statistical learning or like Bayesian influence and so on. So we will talk about those and and that is actually one major part of that. I guess these two already cover like lots of the materials, and then I'll give like an introduction, like very brief introduction. I would say like I may take one, two languages as example, or I may be like using something from scratch uh, to do some very simple like probabilistic programming. But I will leave many of you to explore. I mean, deeper into that, like with your projects and also like your homework assignment. For example, like if you want to do the same, I mean, have a problem trying to solve like you some uh, probability problem. If you want to use some of these languages, you can pick a language, or you can use um, of course, like from scratch, you can actually program from scratch even, but you can pick languages like or packages. For example, Leah, I would recommend like highly like for something simple. Um, and you can also use something known as Pyro, let's say. This is like more like from Uber, like that maybe uh, more popular in my industry. Um, and also like you can also like in the presentation you can dig deeper into each of these by going through some of these tutorials, and then you talk about that like in the presentation. And I guess like one added, I would say, I'm not sure, bonus or whatever, you will get much more familiar or an deeper understanding of probabilities. And um, you probably learn this like in many other different courses, but it's very important discipline in engineering, and I guess it's useful to know deeper about that. So wait a sec. I guess I would just pause here. Like I want to see like if you guys have any comments or questions, like anything like concerns, like before I continue. I guess most likely what I will do like in this first class will be just do a review on probabilities. Like I know some of you may be very familiar with probabilities already, but some of you may be getting a bit rusty, or maybe just have one course like, on that and barely touch anything, and then after a couple of years you forget most of the stuffs. So I will just give a review, and for those who are familiar with that, like probably quite easy. But hopefully I will mention something that like you did not aware like in the past, like yeah. So any kind of like questions, comments, or like anything, or any concern about logistic, and and also like the timeline. I guess I will wait until next next week or two to see if you to determine the timeline basically. I have like some, you see online there's like um on my website already showing like which day we are going to do what, but like that is totally tentative. um so this is like here like I have more students in for the last offering, so like we take more times of presentations, but this time I guess we probably can present it into two sessions, something like only need two sessions to do presentation. We can do more like for other materials, like reserve time for other materials. And then like in terms of midterm, like this is not a firm day, so I will check with all of you guys and maybe like in next couple of weeks to see like which what is the most appropriate time. So because it's a video uh, offering, so most likely we will have like a take-home exam, but uh, in the sense I will, it's like I will give it out like just give you an afternoon, maybe just several hours to work on that, and you just like kind of like download that, like the exam will be available like on campus like at a particular time, and then you should submit that like several hours later on, something like that. So okay, hearing none for the moment, so okay, I will just give a quick review on probability now. So let's see, should I start with I don't know whether I should use probably, I guess is I think it's usually it's better for me to sketch rather than using slides. Let me, it's less boring and also it's less uh, let's see, just let me use something plain. So I guess I first of all, like I guess all of you like heard of probabilities, even though it's getting rusty. So you first think of like, okay, what's the motivation of these probabilistic models? So we have these probabilistic models, like uh these tick. So typically like the objective is like we want to, there's two things, right? So we try to, it's always like we try to get some answer or like get some phenomenon from some observations. Um, and at the same time, like there can be either some inherent uncertainty, so that like we don't know like what will be the outcome, deterministic outcome. So either inherent, like it doesn't matter, inherent uncertainty, or even sometimes it's just lack of information, right? So so for example, like mm, for example, if you think of just throwing a dice, if I throw a dice, uh, if I can really get all the dynamics of the dice when I throw it, like how the corner is going to hit the ground, and then like and the spin, like and how much angular momentum I put into the spin and so on, then I can really predict precisely uh, what will be the outcome of the dice, right? But most of the time we don't have that information. The best we can do is like we will just say that would be like equally likely to have like each of these outcomes. And then like for a probabilistic model, like it's just okay, we have something long as the random variable. So it's just uh it can take like different outcomes, uh and non-deterministic outcomes. Uh and we don't know which outcomes you're going to get. Like we call this a random variable. For example, I take the dice example again, like for the dice here. So I can have like 6 different outcomes in LA. And so I can say the random variables here, let me denote by some x here, some big x here. And x that it can have outcomes like 1, 2, 3, 4, 5, 6. I can have each of these outcome here. So in general, of course, I can have the die is like is loaded. So I don't necessarily to have like each of the outcome to have equal probability. But sometimes like it's actually oftentimes it's like when we don't have like any additional information, we just assume that like all the outcome to be uniformly distributed, say, or like all the outcomes to have equal probability. So and then therefore all of them like the probability of x equal to 1 will be equal to probability of x equal to 2 and so on and so forth. So uh this is like one way I'm going to write this like probability some x is equal to something, or sometimes I will write like this like probability like x is equal to 1. This is just denote that like this x is equal to 1. Actually, this may not have a good notation here. Let me cross out this. So this will be a notation we should use. And sometimes like people write this as well, like px1 here. Right? This is like saying that I'm considering the random variable x here. I'm taking the argument 1 here. And this basically the same thing here. Now, when we say probability, it has to be positive. So it's just like the something very intuitive. Like when it's like larger, then we have it's more likely to happen. And the convention is that like when probability is equal to 1, then it will definitely happen. So therefore, like you cannot have the sum of the probability that is larger than 1, or like any of the probability larger than 1. I cannot have. For example, this probability x is equal to 1 has to be like bigger than equal to 0 and less than equal to 1. So if it's equal to 0, it's just saying that like not going to happen. And this is like this will be definitely. So and also like okay, maybe I just ask a very simple question here now. So for a dice here, if I sum over this probability x equal to 1 plus probability x equal to 2, some probability x equal to 5, let's say, and probability x equal to 6. So what should this be?
One.
Yes. Oh, okay. Rather than say it, like please put in the chat because there's no way I can tally it. Like if you just you can say it, but at the same time, please like also like type it on the chat. Yeah. So yeah, this yes. Uh this is question 1 here. Yes. So you're just saying that like when probability is equal to 1 is going to definitely happen. So because like we can only that these 6 outcomes like either of these like will has to happen, right? And they are kind of exclusive to one another. So therefore, like when you sum all of these together, it has to be equal to 1. So this is not just like for outcome like for dice, but it's also like for all probability, uh, all random variable basically. If you have like random variable y, let's say, and if it can have outcome like maybe I write a script y here. So then if I sum over like all the y here in for all the outcome here, so the probability y sum over y is always equal to 1. So this is like this set of all outcomes. Okay, so uh, let's do another very simple kind of like example here. So let's say if I have a jar here, so if I have like let's say like 3 red balls and like one green ball here. So if I'm going to randomly pick a ball from the jar, Okay, okay, let's draw a hand here. So if I pick a ball from a jar, so what's the probability? Let's say this pick, I call it X again. So this is X here. What is X to be like red? Okay, yes, I guess you probably learned that like from somewhere, like somewhere. So here we use the assumption that like okay, we don't have the actually like this the answer you are giving like uh is correct, but like at the same time like there's some underlying assumption like is we already assume, but we didn't mention that. So we can't assuming that like the chance of picking like all four of them will be equally likely. So we are kind of, you're kind of assuming that like I'm not cheating in the sense maybe like one of the ball is more rough, then I can just say just touch it and then I sense that okay the green ball is rougher, so I will just always pick the red ball. So then I can push this probability to one, let's say. But without any additional information, it's fair to say, okay, each of these ball like have equal likely probability. So therefore, the probability of getting this red one will be just like 3/4. So you see, like okay, for many this probability problem, like is highly related to this so-called like combinatory problem, because like by the end of the day, if I make the assumption that like uh, basically the each of the outcomes, if I assume to be equally likely, then this is just become a counting problem, right? So sometime like I actually I should be more careful with the wording here. Usually people say outcome. You see like the outcome here, like X can have two outcomes, right? Outcome either red or green. Definitely in this case, the outcome are not equally likely, right? One is like 1/4, one is a 3/4 there. What I mean is like the configuration are equally likely. So configuration is like more refined uh, in a uh, in a kind of like lower resolution, I should say. So each of these picking, like for example, I can put an artificial number for each of this guy here, right? This can be like ball one, ball two, ball three, and ball four. And like ball one is green, let's say. Ball two, ball three, ball four are red. And then like um I would say like okay, the each of them like picking ball one and ball two and ball three and ball four, each of them will be equally likely. So each of this configuration will be equally likely. Now, so let's look at another problem, another question again. So say I have now here I'm testing your combinatorial kind of like knowledge, I would say. So let's say if I have like student A, B, C, D, now they can randomly uh, line up in a world. So I can have like A, B, C, D, B, C, D, A, and so on, and randomly line up a world. So what's the probability that the this lineup, maybe I call it maybe big L here, will be precisely A, B, C, D? Yeah, you need to do some counting for this one. Yes. Anyone else? Yes. This 1/24 is correct. So this is like basically doing the counting here. So you're thinking, okay, how many different configurations I will have? And I will assume each of these configuration will be the same. I mean, it will be the same, meaning that like we'll have the same probability. So if you just count it, like you can try to count it. So let's say I start with A, like for everyone start with A, right? I can have like starting with A. Then if I start with A, how many different configuration I have? Like I have like A, B, C, D, A, C, B, D, A, or let me put it this way: A, B, C, D, A, B, D, C, A, C, B, D, A, C, D, B, and so on and so forth, right? And actually, um, okay, let me continue this first. So then, like, you see, like, I can start with A. If I do all this counting, like how many different combinations I have, I can start with A, or I can start with B, or I can start with C, I can start with D, right? So if I think of this as one group here, I have four groups here, right? So I have four groups here. Now, out of these four groups, let's say just consider the A group here, the group that uh, the first student is A. And then look at the rest of the students here. Now I have like three students here, right? And again, like, I can think of like how many groups I have. Like I can have a group that like start with B. I'm a group student start with C. I have a group of students start with D here, right? So I have like three different groups here. And again, I pick the A B group. Like let's say I pick A B group. Um, and then if out of that, I can have like C D or D C, right? So if you count like this, what you see is that like, yeah, that's exactly like say just 4 factorial. So you have like the first one, you have four group here, right? So you have four, and then you look at the next level, like you have like three remaining here. So I have like times three, and then like the next step, I have like two remaining there times two, and then I have times one. So therefore like that would be like 4 factorial, so many like combinations. So just to check your understanding, what if like I have instead of A B C D I have A B C D E F, so what will be the probability that like I line up precisely A B C D E F? This is probably a question before here. Oh, I guess yeah. So you have to be careful. Like I add two students here, so now I instead of four students, I here like I have like 4 factorial, so many combinations, right? So here I add like two students, like more like it's A B C D E F. It's not A B C D E, so it should be like 6 factorial, so many of students here. So yes, so therefore it's like 1/6 factorial, or like 1/720. Yes. So yeah, this is like something like quite simple, but like yeah, quite simple, but is can be very helpful, like actually. But let's see. Let do, and let's give look at another example. You will see like why this is useful. For example, like if I have now again like this A B C D EF like 6 students here. Now I'm going to randomly split them into 2 groups, like so I can equally size group. So maybe team A, team B, I just separate them into 2 teams. So and again, I will assume that I randomly pick students. I pick students. I put one team, another students, group of students into another team. So what's the probability? Like I precisely have like team, maybe what do I call it? Team red. Let's say team red is like ABC. Let's say team red is ABC, and then I have like team blue is DEF. So this is red team, and this is blue team. Actually, maybe I make it too big. Let me make the problems a little bit smaller. Just 4 students, maybe say just 4 students here. So let me 4 students. So probably will be easier for me to explain later on. So let's say what's the chance that I exactly get like students A, B into one team and then students C, D into another team? Okay. So anyone give a try. So think of that like you can try to okay. Some of you may know that right away if you uh uh actually I put in the way it's maybe a little bit more trickier. So maybe you probably know the answer if I say what I'm doing is essentially okay. I'm thinking like I'm splitting into 2 teams, right? So think of like how many combination can I have if I just here if I just pick like 2 students out of this group of students here and put them in the red team here or like into the blue team here. So how many different ways I can like pull out 2 students here and put into the blue team? And that would be like the number of combinations, right? But on the other hand, what I want to kind of um, guide you here is that like you see like pulling out formula is great, one way to do it, like uh but it's always like if you have like more ways of like thinking of something like the deeper the understanding of something. So from like what we learned just here, you can also think of another way is like trying to do counting like from first principle, and you will get the solution as well. And actually from that like you will see why we have the formula like Sarah just mentioned. Uh, uh, 1/12 probably is not correct. But my my mind my computing power using uh, mind and brain and paper alone are pretty bad. Uh, 1/24 is will be okay. This will be you will essentially saying this will be the same same number of like combinations as this guy then, because here like there's 1/24, so different combinations, right? And for this one also you counting the number of combinations here. I would say there will be fewer because I if you think of that, like if I pull up a um this is like counting all the configurations. I have like 24 of them, right? So if I count like A B C D, A B D C, A C B D, and so on and so forth, there's 24 combinations here. But if I here I'm just trying to count like how many combinations of like pulling students into one team and another two students in other team. So know that like I can have a configuration like BACD is the same as this guy here, right? Because like these two, like ABCD, if you think of like aligned students in a row, yes, that's good. Yeah, that's good. Yeah. Um. Yes, you can. Yeah, actually, I think you will get 1/6. Um. Yes, you're just caring about like what. So you need to be careful. Yeah, actually, I guess like one thing about like solving this probability problem is like first understanding that what's the problem precisely, because like that can get quite tricky sometimes. So here, like we just care about like whether like someone is in the red or like someone in the blue. So we can do first principle as I mentioned. So now if we think of that like listing all 24 like combinations here, right? If I list all 24 combinations here, I have like 24 combination. I have A, B, C, D, A, B, D, C, A, as A, C, B, D, A, yeah, A, C, D, B, and so on and so forth, right? Now, if I think of like out of this 24 combination, how many how many the configuration I can group into one team? I also would depend on how the sets are picked. Uh, mm, no, actually, uh, what we can do is like just do counting. Like here, we basically what we what you can think of is like let's just count it like how many different combinations I have, and see if like all these combination should have like same probability. If they have like same, if I assume like each of the, for example here, I assume like the way I'm kind of like putting students like into two team. One way I can think of like okay, let's line up each of the students like randomly. After they line up with one another, I'll pick the first two students into one team and then the next two students in the other team. So then for these 24 combinations, like all of them will have same probability, right? Now let's think of like out of these 24 different configurations here, some of them actually will correspond to the same team outcome, right? Because apparently I have like A, B, C, D, and A, B, D, C. You can also think that way, actually, but you're thinking like taking A, B first and taking C, D first would be the same, right? So that would be the second solution. Okay, let me go to the second solution. It's easier that Sarah mentioned or hinted on. So it's essentially, let's think of like I have two teams here, A, B, and C, D, right? I can either think of, okay, let's pull out two students randomly and put them into team A, or sorry, team red, and then the remaining student into team blue. Then I want to see like how many different combination I can have, right? Then that would be like this 4CR problem, right? 4C2. So it's basically out of these four combinations, okay, four elements here, I randomly pick two, and I want to see like how many different configurations do I have. So then would be like this, just give me 4 factorial over 2 factorial, 2 factorial, something like that. That will give me 6. So since I have like 6 different combinations, and I believe like all 6 combinations, like 6 different outcomes should have like same probability. So therefore, like it would be 1/6. So this would be like a quick way for this question to answer this question. So another way I can do a first principle, as I just mentioned, right? I can list all the combinations here. So I just think of, okay, I will line up all the students here randomly, and then I pick the first two students as team red, and then the second two students as team blue. Now, then if I look at the combinations here, I have ABCD and ABDC will be the same, right? So they belong to the same team. And also like I will have also like BACD and BADC will be same team, right? So therefore, out of these 24 configurations, I should I basically overcounted like by 4, right? So therefore, like by 4 times. So I should divide 24 by 4. So again, will give me 6. And how do I get this 4? Because like for the first team here, I have two members here, and I can kind of like arrange them in any orders. This gives me like 2 factorial, right? And also like this gives me another 2 factorial here. So therefore, like will be divided by 4, and this 4 is actually equal to 2 factorial, 2 factorial here. And the original number of configurations here is basically 4 factorial, right? And this basically gives me back the 4C2, that kind of like formula there. So, uh, and hopefully like I make myself clear. So let's just make sure that I'm clear. Maybe I just make the problem a little bit more challenging now. So I have A, B, C, D, E, F. Again, I group into two teams here, A, B, C, and D, E, F. So what is the probability that I have a red team of A, B, C, and a blue team of D, E, F? Oh, that's great. So how about this one? So now just make the problem a little bit bigger. Yeah, I think you guys are probably correct, but let's see. You know the Pascal triangle, right? Sometimes I don't know. 151, 14, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6. I think it's like, did you, it's like 6, C3, something like 6, 15, 20. Yeah, 20. Yeah, that's is basically like 6 factorial over 3 factorial, 3 factorial. You can ignore what I'm doing here, but yeah, that's basically, yeah, that's 20. Yes, is correct. So in this case, I will be just like, you can think of, I pull out randomly, like pull out 3 students here out of 6 students, and I see like how many combinations do I have. That would be like 20 different combinations. So therefore, like the probability will be 1 over 20. Yeah. So but I only see like 3 of you guys are answering. So for the rest, I do you have like some questions, like with the, or you guys are still around? Yeah, just let me know if you have kind of like anything unclear, so we can. It's a small class, so yeah, we can always like pause, and actually also like whenever you have a question, that's most likely like your peer also have a similar question. So please don't worry to ask, like yeah. And if you want to, like, you can even like send private message, chat message, like to and okay, that's fine. Yeah. So okay, let's move on then. So now let's think like this. Let's go back to our original, not original, or like the earlier setup here. Let's say I have like a jar here that have, maybe I just copy paste it and I don't need to draw it again. Maybe make a new page here. Let's consider jar, a jar with balls again. And let's say I call this a, oops, I don't want to change the color here. So, okay, let's call this a jar A here. Now, let's say if I have a jar B here also. So I maybe, let me copy again. So, but for jar B here, let's say I have like 2 green balls and like 2 red balls instead. Okay. I have one jar is I have 1 green and 3 red. And another jar I have like 2 green and 2 red. Now let's say I'm going to randomly, okay, what the procedure will be like this. Let's say someone is going to pull a jar out of a box. So and the jars can be jar A or jar B, and there's no label here. You don't know whether you're pulling out a jar A or jar B. And then once you pull the jar out, and then you draw a ball from the jar. So and say like here also, like these 2 jars will look identical, right? So when I pull out the jar, I don't know. You can assume that that's equally likely, like pull out jar A and jar B. So what's the probability? Let me use back again. What is the probability that I will Let's see. Let's see what. Okay, let's ask this. What's the probability that I pull a jar A and also like I pick a wet ball, jar A and wet ball. This I don't know which question now. There's some other question here. Okay, I guess that's very good. Yeah, I see that like I don't know Amy's answer. Like I don't know where you get it. I'm not even sure it's correct or not. Let's see. 10, 24. It yeah, it doesn't look like it's right. So um so, let me try to explain for some of you, I guess that gave the answer like a 3/8, and I see if I can explain the logic that like everyone is happy about that. Oh, you cannot add them. The problem is that you cannot add them. So when you add the probability, you need to make sure the event are exclusive to one another, or the outcome is exclusive to one another. I guess in this case you cannot exclude. Yeah, you can double check, but like when they are not exclusive to one another, you cannot add the probability. So if you say yeah, okay. So let's go for the logic of like I guess most people like answer correctly here. So that like okay, we can just assume like this is like equally likely to pick jar A and jar B. So then like the probability of jar A. So I will have the probability of jar A, right? There's 1/2, and then like knowing that like I'm picking from jar A, the probability to get a red is 3/4. So I have like probability of a red given jar A. Do you agree with that? That's basically how we get that, right? So and by the way, this is known as the Bayes rule. Even though like often you see that they represent this way, like probability, some conditional probability, for example, in this case, like jar red, red, give the ball red given jar A is equal to say probability that jar A and wet over probability dry A. So like you probably see this form before, like this is known as the base rule. This is how you get the conditional probability. But I guess intuitively, I think this is even uh, more natural because I see like if you are asked a question like this, you write this right away without hesitation. Most of you did that. Um, and you are already using base rule, and I'm not sure how many of you are realizing that. Yeah. Oh yeah, no, yeah, no. Sorry, like it's dry and dry B. I guess I just misspoken. Like yeah, there's two jars. They're they're non-distinguishable. So like and equal likely to pull out of this box, and then like dry have like more red balls here, and dry B have like less red balls here, and then like just yeah. Okay. So, and you can actually create a training rule in general, like for base rule here. For example, like if I have the probability, I have uh, several random variable here. So you can think of each of these are random variables, right? So let's say if I have like random variable x, y, and z, x taking outcome x, y taking outcome y, z taking outcome y, z here, small z here, the probability will be okay, I want to be consistent with my notation. Probability x times probability y given, sorry, I mean this I should put y given x here, small y given small x here, and then p uh, z given x and y, c given x, y here. And you can have more basically, or I can write it another way. I can start with just a z here, c, right, and then p y given z, y given z here, and p z given sorry p x given y, z x given y, z here. Again, like this is, I guess it's very intuitive, but at the same time it's very useful, and I guess seeing this training rule form is much more uh, intuitive, also like kind of convenient than the base rule you usually see in the textbook. Like usually they have like just write it as a almost like a definition for the conditional probability. Uh, on the other hand, like you see like in many problems, like actually it's the conditional probability is given, right? Because here, like for example, this problem here, you are actually already given the conditional probability. Given is in dry A here, you know that the probability getting a red or green will be like this. So you don't need to have a definition to, yeah, I mean, what I mean is like, oftentimes it's not like you don't have this. I mean, I need to find this like out of these variables here. Of course, like that's a situation like this, but also like there are many other situations like this problem here. You're actually given the conditional probability here already. You know what's the conditional probability? Then maybe you want to find the joint probability or something like that. So here, maybe like I just ask another kind of continuation of this question here. So what's the probability getting a wet then? Out of this procedure? Yes, Sarah has an answer. Like anyone else want to give it a try? Yeah. Yeah, I think like most likely, 580 is correct. I'm not 100% sure yet. Maybe not. Let's see. Uh, let's try to do it together. So, um, we computed this one already, right? So maybe I just write this more form or kind of like more precisely as like maybe p jar taking an a, maybe I like this p jar, and the ball, maybe jar and ball, I get a and also like red, right? So that's the probability is this guy here, and this eventually is equal to what's that again? Like 1/2 is 3/8, right? 3/8. Now I can compute a similar probability that like what's the probability of like draw and ball. Let's say if like I have draw is from B, and then the probability also, I mean I'm also like the ball is red, and but the similar token is will be like equal to probability of draw equal to B. That's basically 1/2 times a probability red uh, given jar equal to B, and this is basic 1/2 again, right? For jar B, I only have like I have equal likely to get a red ball and green ball, so therefore this is a 1/4. Right? Now, then this is a actually I can jump. I guess you guys know this. I had like so it's a this is known as this marginalization, right? So if I have the probability xy, or like maybe I have like yeah, okay, probably xy, and my sum over like all the outcome of like one variable, let's say xy, I sum over all the x here, so over all this set of all outcome of x. So this will give me like just py of y. So I just marginalize, I just remove one of these variables here. So in this case, like jar can only have two different outcomes, like either jar A or jar B, right? So therefore I have like, I should have P probability of red here should be just equal to this one plus this one. Right. So therefore it's like 3A plus 1/4, so it's like 5A. Yeah. So this is correct. Right. Yeah. So so actually we already okay. This is nice to kind of review this marginalization if you're not familiar with that, but you see that you sometimes you're not familiar with that, but like you're using that anyway. But this that's good. Yeah. So let's see. We mentioned this here and also mentioned base rules already. Let's see what else I want to mention here. Okay, maybe ask one question more. So what will be the probability of jar equal to A given that like ball is wet? So it's asking backward now. I guess you have all the components here to answer this question. So you just want to kind of like putting things around like, and you have the base rule that's most important. Not I shouldn't say most important, but for the base rule, it'll help you to know okay what will be this conditional probability, right? And then you will be able to find uh, each of that and to compute the value here. And this is a this kind of like problem actually occur quite often. So you can think of like this is will be like eventually see whether the ball is red or green will be some kind of observation, and then you want to see like get some hidden variable. Like for example, in this case, like each which jar you pull out, like it will be like some kind of hidden variable. Uh, and and out of like which ball you pick, you can say like whether it's yeah what would be the chance that you're actually pulling out from uh, a particular jar. So okay, I guess I will let you guys play with this. Maybe also at the same time, let's take a break. Maybe we'll come back like 4:30, and so we will have your answer, or like we'll talk about the answer for this one. Yeah, and so sorry that like, I'm having a break, but I leave this question to you. Like not. Uh, yeah. Okay. And yeah. So if you need a longer break, it's good to me. Yeah, like 4:30 is okay, or like I should make it a little bit longer. I don't know 4:35 or whatever. I hear no response. 4:30 work. Yeah. So okay. Yeah, I'll see you guys at 4:30, and then yeah. let's resume. Um, and okay, let's. Oh, actually, before I continue with this, for this one, I guess some of you already like give an answer here. Um, I forgot to mention Discord. Like, so what we're going to do, our main means of communication, like either private or public messages you want to send to me, like please send it through Discord because um my email box after so many years are loaded with like junk mails. I always uh there's a very good chance I'll I mean like I would say like a very good chance, but like there's a chance that I will miss your emails. And also like it's harder to track with emails. For example, if we back and forth like several emails like a couple of times, already you kind of forgot like what we discussed at the beginning. So, but if you send a message on Discord, like you see like everything is like, um, I mean, the past record is right away in the message, so it's just much easier um to follow. And and also like yeah, I would encourage you guys and maybe make it a homework zero or something that like uh please introduce yourself on Discord. Like you already find the sign up link like on Canvas. I see like some of you already um signed up like already like and you can just post a message in the under the maybe I guess there's a journal or something like uh session there. You can just say maybe post a short introduction there um, about like kind of like what area you are from, like maybe and like what major you are, and then like if you're doing some kind of research, like what particular research you're working on, and so forth. And I guess like that's very helpful, like not just like for me to know better about you guys, but you guys can kind of like have better chance to collaborate in the future, uh, not just for course project, like for this class, maybe like in the future, like you guys can team up together and work on something else, maybe create a startup like among yourself or whatever. So yeah, please like I guess I'll formally post on Canvas. I just make it like some small points you can get like for putting an introduction like on Discord, so that like, everyone can see that. So okay, now back to the materials here. So this one, okay, should not be very difficult, should be quite easy. Uh, so using base rule, okay, again, I think of like base rule as some kind of chain rule. So if I have this, if I also multiply by probability b equal to red, oh, okay, wait a sec. Uh, uh, let's see if I missing a chunk from the left side of your screen. It's great though. What's that? Let me stop sharing and share again. Share, share. Do you still like what is this? Let me pull this out. Still gray. Okay, let's see if like what's going on here. If I move to another screen. Oh, okay. Yeah, it works now. Oh, okay. Yeah, I don't know. Like maybe just. Oh, thanks for letting me know. I guess I maybe I don't know some kind of like bug for Canvas. For Zoom. It's okay. So uh Okay, for this conditional entropy, if I multiply by this guy, I will have the John probability. No, so what I'm saying, conditional probability. If I multiply with this guy, I will get the John probability here, right? Be what? So, therefore, like, okay, this one should be equal to this one over this guy, right? Over this guy here. So I pull this from the left hand side to right hand side. And probability of what we got it earlier is just equal to 5/8. And then the probability, this guy, I guess we computed earlier, is this one, dry A and wet, that is equal to, where's the number here? I guess it's 3A if we didn't write it down here. It's equal to, this is a 3/4, so this is a 3/8 here. So therefore it's a 3A over 5A, so it's a 3/5. Yes. Okay, maybe a quick question again. So how about dry equal to B, given the ball is wet? So you should get this right away. What would be this value? Yes, yes. Yeah, because the draw can either be A or B. And then like these two add together should be 1. So therefore this is just equal 1 over. So it's like 2/5. Now, know that, like, be very careful. Like this, if I ask you jar equal to A, given ball is equal to, what's the color I have? I've got like it's red and green. Yeah, green here. So what will be the answer for this one? Oh, that's quick. I don't know. Maybe yeah. uh, it will need some time for me to compute basically, but I trust you guys. The point I want to make here is like this is a mistake that I did like when I was a grad student. Like I get confused. Like for example, x given y plus p. Oops, I don't know what's x given z. Or okay, or maybe like this kind of stuff. Like so, know that I have this sum over x is equal to 1, but we cannot claim anything like for x given y sum over y. So this I don't know what is that. Actually, it can be bigger than 1 or whatever. Like it can. This is this doesn't necessary to be like less than 1. So this can be bigger than 1. Of course, it will be bigger than 0, but like I cannot say like it can be like smaller than. It can be smaller than 1. It can be anything basically. So okay, since most of you guys I computed that, like, let's see like what should be the answer for this one. So we can repeat that. So it'll be like is equal to probability A and ball is equal to green over probability ball equal to green. Okay, probability A and ball equal to green is, let's see, this one is equal to jar A is 1/2. Probably ball green is a 1/4, I think, right? This is a 1/8. And then we also need to compute like probability jar equal to B and ball equal to green. And that give me 1/2, and this is 1/2. That is basically 1/4. So therefore, like this one is I add together is a 1/8 plus 1/4, and this is 1/8. So 1/8 over 1/8 plus 1/4. I think it's 1/3. Yeah, several of you get the correct answer. So okay. Yes, I guess that's nice. That's because we already covered like base rule, marginalization. Okay. The next thing I like to kind of reveal, like I guess many of you should know that already is like expectation. So we say, oh, actually before that, like before expectation, I need to talk about probability distribution. So actually we already using that. Like so we say like a distribution, let's say with a random variable x, px, we're already writing that this is only a distribution. So it's essentially it's the function of the probability with respect to different outcomes as the argument. So it's the function of the probability with all the outcomes. So and if the outcomes are discrete, as what we did in the examples, we have this known as the probability mass function. So if a random variable is discrete. So in this case, we have basically this will be sum up to 1, right? So I sum over all x here will be all sum to 1. However, if my random variable is continuous, then basically like I have infinite number of outcomes, right? So what, for example, let me give an example here. Let's say x is today's temperature or like current temperature, right? So the current temperature you can think of like in let's say Fahrenheit, it can be like maybe 80s or 90s. I don't know what. I am not bad. I'm not exactly sure how hot is today. So, but it's like a continuous number, right? So if I say like the probability of x is equal to exactly 80 °F, so it can be always equal to 0 because you can claim that like when it's like 80.0001 is not equal to 80, right? So, and therefore, like if you want to have a continuous random variable to be exactly precisely equal to some particular value, the probability will always be equal to 0. So instead, like we should ask about a range. So what is the probability of x is within a range? Like for example, like 80 plus some delta and 80 minus delta. Maybe I can have the delta is equal to 0.1 degree, something like that. What's the probability that like I have the temperature say from 79.9 degree to like 80.1 degree? And then so since we cannot precisely define the probability or like precisely write down like the probability of some random variable equal to some precise value that basically is always equal to 0. So we cannot define the PDF or the probability. They call it density function. How now? Probability mass function. Oh, sorry. Like this is the distribution, but the name of the distribution is this function here. Usually called like probability mass function. PMF. Wait, PMF. I'm sure you see that before. And when it's continuous, like we call this. I didn't define it yet, but I will basically, because this is always equal to 0, but instead I will take a limit. So I will just see like the density of that, like how likely I will have the random variable that will kind of get near to that range. So then I can define, for example, like p x 80 as like taking the limit of delta go to 0, this over delta, something like that. Actually, in this case, I should put 2 delta here, or I put delta over 2 of delta over 2, something like that. And this I can define a probability density function. You can see the physical meaning of a probability density function will be like that way. So if I have like, for example, like for the PDF of the temperature I just mentioned, maybe it's in the summer, I have the peak is around like maybe 82, I don't know, degree or whatever. And then like you see the for a particular day, what's the probability to within like this particular range here will be just the area underneath this curve. So this is like basically the PDF, like this is a PX X here. So for example, I have this is 85 to 90. So the probability of X from 85 to 90 will be just equal to this area underneath. So it will be just equal to the PDF X taking the integral from 85 to 90. So therefore, like for continuous random variable, let me erase this part here. For continuous random variable, instead I have like the sum of the probability mass function, like in the discrete case is equal to 1. I have the integral instead like is equal to 1. It's equal to 1. Yeah. If I kind of integrating over the entire real axis, let's say, or like all the possible value of x. So this is a PMF and PDF. By the way, like in many books, they will use PDF like to use a F instead. Fx, X, something like that. Like here, I won't distinguish that. Like just like some of the textbook, like they would just use like P for both like PDF and PMF. So I won't, because like for the context of our discussion, it's not important. Like doing PMF, PDF. Like most of the case will be, and actually most of the case that you can understand the concept like sufficiently, like using PMF alone. So I oftentimes use PMF as an example. So, but okay, so this is about the PMF and PDF or the probability distribution. Now, then let's talk about expectation. So, we say have a random variable x. If I have a function upon x here, for example, I have fx here. Note that fx now is also a random variable, right? So because like x is random, fx here is also random. So we can take different outcomes here. So let's say f, I can x is like originally can be like, actually, for example, like I can have x is like, for example, like the ball, the color of the ball here, it can be either red or green, right? So therefore, like this doesn't necessary. This random variable doesn't necessary to have even like to have a number as its outcome. But let's say I can map x into fx here. Fx, let's say is like it take like values as outcome. Then I can define the expectation fx just as the the average of all outcomes for this distribution. More precisely, is like is equal to px x fx sum of x. If x is a discrete random variable, so if x is discrete, So if x is continuous, then I will have like e f x is equal to integral instead, right? So, but the point is that you just think of like what that's just as the name suggests, like what do you expect, like, right? So if that's is like the expect will be like what on average what do you get? So given the random variable, if I map into some value, what do you get? Like what do you expect the average value will be? And then like if say if x itself is numerical, then we can simply compute like expectation of x. That would be just equal to the average of x, right? It would be just equal to mean. So that will be just give me the mean here, right? And sometimes people will denote that with just like x bar here, which just give me a mean here. Maybe I should probably pause here like to make sure like you guys are following me. So let's see if I just give an numerical example here, couple numerical example here as questions. So let's say question one here. I shouldn't say question one. Some question here. If I have the dice, right, can have outcome 1, 2, 3, 4, 5, 6, right? So if this dice is unbiased, it's not loaded. So what is the, let's say the outcome of that dice is just x. So what is the expected value of x? You may need to compute that. Yeah, it's close. Yes. Yes. Uh, yeah. Okay. Yeah. I think it's like quite simple, right? So yeah. Oh, okay. The question is like we here like we give the definition of expectation. Also, the meaning of expectation is like you can think of like what's the f. You can think of this as average um of that value. So and will be just defined as like this here for the discrete case. Now, if I have uh, the random variable is just the outcome of the dice. So the dice can have like outcome 1, 2, 3, 4, 5, 6, right? So and I assume that like the dice is unbiased. So therefore each of the outcome have are equally likely. Then what will be the expectation of x? So what is ex here? This is a, yeah. So okay, maybe I would just say give out the solution to see like if it helps. So I just follow this. So uh, uh, so basically like I have expectation of x like by definition will be just equal to sum of a px x Okay, let's think of this as fx here, right? So if fx will have a definition like this, right? So I have essentially f is an identity function, right? So therefore this fx here becomes just simply ax, right? So therefore it will be just equal to x x p x x x here, right? And this x here is can be 1, 2, 3, 4, 5, 6, 6 values here. And all of this is equally likely. So all of this is just equal to 1, 6. So I will have like 1, 6 times 1 plus 1, 6 times 2, and so on, up to 1, 6 times 6, right? So then you will basically get like 7. Okay, 1 plus 2 plus 3 plus 4 plus 6 should be 6, 7 times. Wait. What is that? Like 6 times 5 over 2. Yeah. And then like over 6. So it's a, oh, I made a mistake, I think. Yeah. 1 plus 2 plus up to 6 should be like 7 times 6 over 2, I guess. So it's like equal to, and then I need to over 6, right? So therefore, like this, I got canceled. That would be a 3.5, something like that. And if you don't know what I'm doing here, it doesn't matter. You just like put into calculator, it should give you 3.5. Yeah. But yeah, if you just look at that, this is exactly 3.5 in the middle, right? So on average, like I have like this, all of these are equally likely, then it looks like it seems like you have a ruler here, you have a bin here, like a point 1, another b here, you know, point 2, 3, 4, 5, 6, like here. And then you want to see where the center of gravity will be, like precisely here, 3.5, right? Yeah. So, okay, let's do another numerical example. So just to make sure that you caught me. Uh, so, and let's say now if I have some students, let's say, uh, um, I'll just assume their height with kind of very idealistically distribution. The height will be like uh from 170 to or like 165 to 185, like the height. Okay, sorry, like this is centimeter. I'm not used to, I used to metric. I'm not quite used to feet also. So anyway, let's say like this is like the distribution of a bunch of students. Like they have their height, have a distribution like this. Now, what was the average for that? Or like I should say, like what's the and the students, if I pick a random student here, they will have the height like within this distribution, right? And I say like the height here will be h. Let's say it's a random variable, saying that like, meaning that like h can have a distribution like from 165 to 185 and uniformly like for all this value. So what will be the expectation of h here? Yeah. Actually, you can see where away in the middle will be 175. And of course, you can compute also like just like this. So you have is ph small h, um, and then h, right? dh, take the integral. Now I need to take integral because it's a continuous random variable, right? I know that there was ph over h here. So everything here is normalized to 1. So therefore, like the entire area, the area like from 165 to 185 here should be equal to 1 here. So the height here should be like 1 over 20, right? So height here is 1 over 20. So this should be equal to 1 over 20. And then if I take the integral here, say 1 over 20. So it's just I can pull it out, I guess, 1 over 20. And the h dh is at 165 for 185 here. So this I take the integral is h squared over 2 185 to 165 over 20. So it should be 1 over 40, 185 square over 165 square. Okay, hopefully this should give me 175. I'm not 100% sure, but yeah, if I didn't make mistake, it should give me 167, 175. Maybe I should really put in a calculator to make sure. Oh yeah, okay, it's 175. That's good. Yes, so you kind of know what expectation mean and also average. Maybe I should give a couple more examples. So I have like f here is just an identity function, right? When I compute the mean. So how about if I want to compute the variance? So this is the mean. Let's variance. So variance is like trying to kind of estimate the spread of a distribution. So a high variance means that like the distribution is more spread out. So if the variance is smaller, then it's like less spread out. So the definition is something like that. If I have a random variable x here, the variance is a expectation x minus x bar. That's the mean square, something like that. So you see that like if I have the random variable here, how is differentiated from the mean, right? So for example, I have distribution here, the mean is somewhere here, right? So if it's like it's more spread out, then I will have this value will be bigger, right? I'm taking a square here. This is I just always make sure this is positive. So I take the if it's more spread out here, like I will have this variance will be bigger. So if I have like a more if I have a distribution is like sharper here, then I have this each of this x vary from the mean will be smaller. So therefore, like the variance will be smaller as well. I guess like this is one of these equation you should remember, like variance. So it's a simple and kind of like if you think of that, like uh, for example, if you're trying to like measure what is the how the distribution is how much a distribution is spread out, and you're trying to define a metric to quantify that, it looks like this will be the simplest thing you can imagine, right? Because you want to see how far is from the mean, and you can take this, right, x bar, take the absolute value for that, but the evaluation will be very difficult. So therefore, like let's do the square instead. I mean, it doesn't make sense to have like higher order, right? You can do it, but what's the point? So therefore, like this is a very natural definition. Now we have the variance for this guy. Maybe like let's try to compute the variance for this one. So another question here: what's the variance of x for the dice problem here? So you guys are still around? Like you following like what we're trying to ask here? Okay. Yeah, someone have an answer. So definitely I don't know the answer on top of my head. Like I need to like compute that as well. Let me put it on MATLAB and compute the numerical value here. Um, yeah, my value is a bit different. So I can double check if another. Mm, probably not. Yeah. Yeah, if I'm cheating, basically, I'm using MATLAB here. I'm kind of like for this kind of compilation, I say, um, it's a no, I'm not showing the result of here. I'm not, but I'm saying like I'm kind of cheating. I'm not sure how many of you are using pen and paper, but I'm just using MATLAB here. Um, more precisely, I'm using Octave. Yes, I think that answer, last answer is correct. Yeah. So you want to do it like from first principle here, oh, like if actually this is always a good way to kind of start with a problem that in an area that you're not so familiar with. Like we can just start with the first principle, right? So now I know that like okay, the definition, let's say for expectation fx is equal to like pxx like fx, right? Sum of x here. Now let's see, I just look at each of value of x here. So x equal to 1, I know this is a 3.5, right? The mean is 3.5 here. So when x equal to 1, I have like minus 2.5, right? So minus 2.5 square. And then the probability of like getting that is a 1/6, so over plus over 6 here. And then like when value is 2, then I have like minus 1.5 square over 6 here, right? When value is 3, I will have like minus 0.5 square over 6 here. Yeah, yeah. If you use, yes, 0.5 square over 6 plus 1.5 square over 6 plus 2.5 square over 6. So if if your calculation is correct, then this should give you 2.91, something like. And let's do this also, huh? Let's, for this example here, we have like used the same example here. We have this distribution for the high tier of a group of students, say, to have uniform distribution, like from 165 to 185. So what will be the variance of H here? Yeah. So this is another question here. So what will be the, oh yeah, that's actually that's the thing. Like it does not depend on how many students here. It only matter with the distribution here. The distribution is uniform from 165 to 185. So remember that like for continuous case, so you have, yeah, something like the definition. It'd be like that to compute the expectation. Yeah. Yeah, the value is probably not as nice. uh, yeah, that one maybe. Yeah, I don't know. Like I need to. Uh, I don't know that on top of my head, honestly. Um, yeah. So, but we can again. I just look at this first principle. Like I have fx here. Now the function is I have this as the function, right? So and I know the mean is 175. So then the expectation of fx, oh sorry, like in this case is a fh or like fh, maybe I call it this or like, yeah, okay, let's keep it fh here, or like this fh is actually h minus h bar square. So it's equal to uh, the probability distribution, as I mentioned, is uniform. Like we mentioned, it should be just 1 over 20. So this is just a constant, it's 1 over 20 here. Fx or like fh here is just h minus 175. Oh, by the way, you see that like I assume the variance is less than half the spread. No, actually, I don't think you can assume anything like that. It's like um I doubt you can do, because like for example, like you can have like real distribution that like you can have, if you define the, for example, the spread as the more precisely as the what do we call it, the what do they call it, control, or like I forgot. So in the side the part is like, or only for uniform, that may be, I don't know. Yeah, if it's like you know that it's a uniform distribution, that may be, but I don't know, it's not on top of my head. um So, but let's not, don't make any assumption. Actually, it's better not to make any assumption. Like if you never see that before, yeah, uh, yeah. But actually, this is good way to try to think about. Okay, like will there be any kind of theorem like this or that? Like, well, I'm just saying that like before you prove that, you probably you can guess many stuffs, but then like uh oftentimes, because I did it yeah, like oftentimes as well, I try to guess like some of this film, but it turns out usually I say that they are incorrect. Like there's always eh, some special case that will violate my claim. So okay, back to this one here. So it'll be something like this. So I trying to compute this 165, 185. Huh. This will be equal. Okay, if I take the integral, it will be h 175 cube over 3. I guess if my calculus is still good, so it will be something like this, right? So the value should be something like that. Let me try see. So therefore, like okay, let me substitute the value anyway. So it's 120. Um, let's see, 1 over 60. 185. So it's a 10 cube, right? Minus, this is a minus 10 cube. So I will have like, okay, so actually p value is pretty nice. Actually can be computed numerically even. So it would be like 2000 over 60. So I think you guys are right. So it's like 100 over 3 is, yeah, it's 33. Yeah, 50. Yes. Um, okay, that's basically something about expectation, mean, and variance. So a remark I must mention here is that like you see from the definition of expectation here, it's linear. this thing is linear. So in the sense, what I mean is that like if I have two random variables, or like if I try to compute expectation of some x plus y, something like that, or like maybe some fx plus gx, let's say. So you see, I will get something like sum over x p x x. So fx plus gx here, right? Then I can split into like sum over x p x x fx plus x p x x gx. So this will be like expectation of fx plus expectation of gx. So in general, like if you have something like expectation x plus y, or like even like ax plus by here, so it should be equal to, you can easily verify that it will be equal to a expectation of x plus b expectation of y. So it's something linear. And this is something important, actually. It's very, very useful. Let me just give an example usage for this one. So you see, like, I guess many of you see that before. Like, if I have the variance, this is the original definition of the variance, right? It's like this. And oftentimes, like, it can be computed like more easily as an expectation of x squared minus x bar squared. So we probably see this equation before as well, right? I mean, this is like some kind of like small lemma that this is equal to this guy. So you can easily show that, like using just the linear property here, right? So I have this guy here. Now, if I expand that, I have like is equal to expectation x squared minus plus x bar square minus 2x bar x, right? So I'm simply expanding this x minus x bar square into this. Now, because of the linear property, I can do expectation for each of these guys. I have expectation x square plus expectation x bar square minus expectation 2x bar x. Now, know that like when I do the 2x bar here is actually just a constant, right? This is a random variable, but 2x bar is a constant. No, be careful, like not to get confused. Like what is random? What's random? What's not random? X itself is random, but if you think of the statistics of x, like basically the mean of x, the variance of x, they're constant, right? Once you specify the distribution itself, then those statistics are constant. I mean, like, or like deterministic. So therefore, like, they are just simply constant. This is nothing different from like saying like expectation ax, and this will be equal to a expectation x, right? So therefore, like, I can pull out those. So I will have like 2x bar expectation of x. But expectation of x is just x bar, right? So actually I have like 2x bar x bar. So it's like minus 2x bar square, right? Now I have expectation of x bar square. X bar square, again, x bar is a constant. It's deterministic x bar square, so therefore it's also a constant. This is actually just equal to x bar square. The expectation of a constant is itself, because if you think of I'm dealing with a constant here, like for example, this is fx is just a constant, does not depend on x. Then I have this, I can pull it out. So it's like c is equal to c sum over x px x here, and this should be just sum over to 1. So therefore, expectation of a constant is just equal to itself. So therefore, I have expectation x square plus x bar square minus 2x bar square. So it's just expectation x square minus x bar square. Yeah. By the way, another remark that you guys probably have learned that before in your stochastic class, but I forgot to emphasize that. They say, you see, I try to be consistent and careful, but sometimes I miss it out. Is I always use capital uppercase for random variables, and then I use lowercase for its realization. What do I mean by realization? Is for a particular outcome of that random variable. So this is a convention that every people use. So therefore, you see, when I sum over the small x, where each of these small x are random, are kind of dummy variable for each of the outcome, then I kind of to intentionally use small letter here, lowercase here. And this convention is good, and I would kind of recommend you stick with that whenever possible. Even though in some discipline, I know that for example, I read the textbook on networking. It's a relatively theoretical textbook, but still for that context, it's not very convenient for them to switch uppercase lowercase when they have too many variables. But for our discussion, usually we don't have many variables. It's good for us to stick to the convention that for uppercase are the random variables, and then lowercase will be the realization of the random variables. Yeah. So hopefully that's clear. And so by the way, I don't know the class time. It's until 6 or 5:45. Anyone can let me know. I always got kind of confused with the 5:50. Okay. So yeah, okay. So I guess maybe last thing I like to review, or I don't know, it depends whether you see this before. Probably all of you see that before, but maybe not in this in this way. Let me put a new page here. So let's talk about independence. And conditional independence. So now if I have random variables, not just one random variable, let's say I have two random variables, x and y here. I'm sure you see that before. When x and y are independent, then we have this pxy, or maybe more precisely, I have p, the joint probability pxy is equal to the product px x times py y. Yeah, that's the almost say in the way definition. At least the first time I learned the probability, people just say okay, independent when they satisfy this equation, and that's it. They didn't say more. I don't know how about you guys. The first time I touch probability, they just say Am I just accept that as a fact? Oh yeah. Then it'll be independent. Yeah, okay, that's obvious. Yeah, but I didn't think too much about it. Why is that that case? So, but if you look at Bayes' rule we discussed earlier, then it becomes very intuitive, like why we have this condition here. So know that like another form of Bayes' rule will be like that, like Pxy xy is equal to Pxx Py x y given xy. This is basically Bayes' rule. So this one, the first equation, only one is independent, right? Independent. Yeah, oftentimes people use this notation to denote like x and y are independent. Use this like kind of like x perpendicular to y, say x and y independent. This is basically Bayes' rule, right? So this always true. Now, so what you see is like if this condition is true, what it's saying is like this guy here, Bayes' rule is equal to Px x p y y, right? Or meaning that like I should have something like py given x, y given x is equal to py y. So if you think of that this way, then independence is very reasonable. So we have independence. Know that we have independence only if like for all x and y here, I have this condition is satisfied, right? This one is satisfied. Or meaning that like for all x and y, I should have this equation is satisfied, right? So how do I read this equation here? So basically this one is like saying that given that x is equal to x, you can think of like, for example, our previous example, I have the jar, x can be like the jar and the ball, right? And then I have the ball is different color here, maybe some color, maybe this time is black here, and given the jar is j here, so this one will be just equal to the probability b to be have a particular color of ball. So we are saying that like, okay, these two events, whether we pick a ball eventually to get what color of the ball, and which jar we are going to kind of pull it, draw the ball from. These two things are independent with one another. If this is going to satisfy, if this is satisfied. So this actually, now look at this again. This is very obvious, right? Because if I satisfy this, it's saying that like no matter which jar I'm pulling from, essentially like the probability to get the ball to be a particular color is the same, right? It doesn't matter like which jar I'm going to pick from. So therefore, like the jar must be independent of the color of the ball. Oh, that does it make sense to you? Like, so if I don't have this equal, so it means that like I can have like, for example, like for some jar, like let's say, for example, jar is equal to A, won't be equal to the probability like the ball is like again like some color. Maybe I stick with the previous example, like the red ball. If this is not the same, then ultimately the color of the ball must depend on which jar I'm pulling from, right? Only if like this is satisfied. Okay, this satisfied in the sense that this is satisfied. So in the sense that no matter which jar I'm pulling from, basically the probability of like getting a particular color will be the same. So then it essentially is in this particular example will be like each of the jar will essentially have the same fraction of the wet balls here. So therefore it won't be depends on like which jar I'm pulling from. Then the ultimate color of the ball will not depend on like which jar I'm pulling from. So okay. I hope I didn't make you more confused rather than I clarify like the thing here. But this is the whole point here, right? So if this is the condition you always see in the past, but if you think of like why I have this condition, it's essentially just saying that like if I have this condition satisfied, I have like py given x, y given x will be equal to py given y. And of course, if this satisfy, then x and y should be independent of one another. And the same case also, like if I have px given y, x given y is equal to px x, then also like x and y has to be independent of one another. So this is independent. I guess I just gave an example like of independent like with the jar example. So I will have like the case of independent if like I have jar A and jar B. And if like both jar turns out to have like same, for example, I don't need to have the same. For example, like I can have like jar A is like this. I have like 1 red ball and 3 green ball. And I have like jar B to have like 2 red ball and let's say 6 green ball here. So for this case, I will still have like independence of like, so if we think of the events, it's like what color of the ball I will get, right? Whether I will get what color of the ball. One event is like the color of the ball, right? It's the ball. The one random variable is the ball. Random variables I have here is like the ball and also the jar, right? In this case, I will have the ball, the final color of the ball, and then the jar are basically independent of one another because the probability of getting jar like to get a red, let's say, given jar A is equal to 1/3, sorry, 1/4, 1/4, a quarter equal to a quarter is equal to probability of the getting ball is red from jar equal B, right? Is still equal to 1/4. And this is also true for like for the green color as well. And so therefore like they will be independent. So that this is independence. And now what is conditionally independent? So I have conditionally independence. I need to I can only define that like with an additional random variable. So let's say I have instead of 2, I have like 3 random variables here. So let's say x, y, and z here. I have x and y are conditionally independent given z. If I have, I don't know how many of you like see this before. Like I'm sure you see the definition of independence for this one, like somewhere, even from some advanced course in high school, maybe. For this one, maybe you didn't see it until later. So it's like I will have like px given let's say pxy given z is equal to px given z py given z. Here I'm omitting this x y z here, like so here is is it's understood. It's like I mean this, yeah. So I'm kind of omitting like just for just like to have the symbol as a less clutter. So this is like typically like how people like put it like how x and y are conditionally independent given z, and this has to be true for like all x, y, and small z here. Now I can do the same argument using base rule, right? So actually, using base rule, what is pxy given z? This one is equal to px given z, and then py given x and z, right? So the condition of conditional independence, meaning that like I should have py given x and z should be equal to py given z for all x, y, z, right? So because like if this satisfy, so and this is always this one like always satisfy, like this is always true with base rule, right? So therefore I will have like this one is equal to this one. This one is equal to this one here. So I have this one here. Again, the same kind of interpretation. Like what do I have here? This is saying that like if I'm given z here, sorry, let me write better. So if I given z here, it doesn't matter like if I know x or not, the probability of y will be the same as even I don't know x. So this additional x doesn't give any additional information for me to know what's the value of y. So this like oftentimes graphically people represent it using something known as a Markov chain. So it's like something like I have this random variable like z here, I have x here, and y here. So you see that x and y are kind of depend on one another, like indirectly through c. But now if you given z, you know z here, then the dependency between x and y kind of like break. Or you can think of like this way, like if I try to predict something of the value of y out of x here, whenever like I'm already given z here, then this is already unimportant, this information, because like y depends on x only indirectly through z. So, but if I am given c already, then x doesn't help me in any way. So let's see if I can give some concrete example. Let's say if I let me just put it this way. Okay, let's I have a coin. I throw a coin, and I got head and tail here. And this I got the outcome I call x. It can head and tail. Maybe I just denote head as a 1 and tail as 0 here. So this is a coin here. So I flip a coin, getting result either like 1 or 0, something like that. Now I flip another coin. And maybe I call this like W. U, I call it U. I flip a coin U here. Again, I got some outcome like either like 0 and 1. Now I said Z is equal to X plus U here. So this is like just a bitwise sum here. So in the sense I have like sum like that. If I have like 0, 1, 0, 1, I have like some kind of exclusive, or like 0 plus 0 is equal to 0, 1 plus 1 is equal to 0, and something like that. Let's say like that. So I have like Z is the X plus U. U is also like a conflict. Also have value like 0 and 1, depend on like it's getting head and tail. Now let me get a y here. Let's do another conflict v. Like this another conflict here. And v also like can take value 0 and 1. Okay, let me write it a bit better. I'm sorry. Conflict. Now I try to make a y as z, y as z plus v here. So now if I'm trying to predict what's the value of y here, you see that like if I know the value of x here, of course it will help a little bit. Okay, by the way, like this con is like totally what I want to say is like totally unbiased, and like actually this is not a very good example because like y will be random. So let me make this a random variable. Is a not this is a biased con. It's a so this is also biased. Maybe I have a more probability to get a 0 than 1. Maybe like this is a probability of 0 is a 0.9. This is a also probability of 0 is 0.9 here. Okay. So for this example here, if like this is a u is a 0.9 to be 0, this is a also 0.9 to be 0, then if my original con or maybe our original x is a value is a 1 here, then I can predict, like you can see that like my probability of getting y is equal to 1 will be basically given x equal to 1 will be larger than probability y equal to 0 given x equal to 1. So just because here I you can think of like this. Okay, maybe this is not very good like to say this is some kind of conflict. You just think of this as I have some like discrete noise, like just add to that, like, and this kind of noise. Okay, maybe yeah, it's better just call it some kind of noise. And this noise it's a very simple binary noise. So I can either like uh flip the value of x here. Okay, let me restart. Like maybe like this better example, better to say like without this con. Like okay, just make x, forget about the con. Let's just think of x I can take value like x can take value 0 and 1 here. Now and z is equal to x plus u, and u will forget about the con. Let's say have a high probability to have like 0 than 1. So it's like just a binary random variable, like with probability of 0 is like 0.9 and probability 1 is like 0.1. And then also like v is a similar kind of like random variable, have the same distribution, have like 0.9 to be 1, and then well actually I'm already kind of almost time. I like to give a summary of like what we just mentioned. Okay, I guess I'll come back to this one later on, but maybe like for the moment, I just want to give a quick summary like what we cover, like then you have an idea what just is like see if you miss something. So here we just trying to give a review of probability, right? Even though we didn't finish like an entire thing. But I guess the first thing we mentioned is okay, like you think of like probability, like oftentimes it can if you assume that like each of the configurations, like underlying configurations to be equally likely, then many probability problem will ended up into some combinatorial problem. So that's we discussed at the beginning. And then we talk about Bayes rule, like using some example like go for Bayes rule. And then we also mentioned like how to marginalizing like a random variable. So if you remember what we mean by marginalizing is like if you have two random variable like joint probability x and y here, then let's see if I can move here. See if I I think it's probably somewhere up there. Okay. Marginalizing. Or maybe I erase that. So, but it doesn't matter. Like, so marginalizing, like I have like P, X, Y, X, Y. If I sum over one of the variable X, I should give like P, Y. P, Y, Y, something like that. So this is for marginalizing. And this is marginalize. So we also talk about expectation, like taking mean and variance as example. And we talk about PMF and PDF. And we just talk about independence. We kind of covered independence now. So, and we are talking about conditional independence. And we will continue with this one next time, I guess. So, yeah, I guess I will just end here. I'm a little bit over time. So, again, as I mentioned, I'll put it up a formal homework seal for you guys to introduce yourself on Discord, basically, and post on Canvas. So I'll see you guys next week then. Yeah. Okay. Yeah. So let me know if you have any questions. Otherwise, I'll just end it in uh, in a minute. Yeah. Okay. So okay. Seeing no questions, I guess I will just end the connection now. Yeah. Sure. Thank you. Thank you for attending.